first problem is we want to talk about this test called the comparison test. Comparison test of convergence. Comparison test. All right, comparison test. And I've got a calculus book here. I've got a calculus book, and they talk about this comparison test. And what this comparison test, page 574. Let's take a look at page 574. All right, page 574. And what this comparison test, it's right here. It says that you've got to have this series, and what you're going to do is you're going to have a B sub n and an A sub n. All right, so what this says, if B sub n converges, then A sub n converges. If A sub n diverges, then B sub n diverges. So we're going to talk about that and hopefully bring a little clarity to this idea. All right, so we've got this problem that I'd like to go through. It is you're summing from n is 1 to infinity this series 2 over 3n squared plus n plus 1. All right, so you want to determine as you count by 1. If you put 1 here and here, you'll get some number. And then you'll add it to putting 2 here and here. You add that to the result of putting 1 here and here. And you continue to increment. You put in 3 and 4 and 5, and you add each of these terms together. And what this exercise is, this is a study of determining, after adding an infinite number of these terms, can you get something finite? If you can get something finite, we call that converging. If this continues just to grow and get larger and larger and larger as you add n is larger and larger number, we say that would diverge. All right, so you've got a series of tests to check this. And right now we're going to talk about this comparison test. All right, so what we want to do is we'll call this A sub n. We'll call the original function A sub n. So A sub n is 2 over 3n squared plus n plus 1. And then what we'll do is we'll call B sub n a function that is similar to A sub n. It's similar to A sub n, but we'll know a lot about the function. This B sub n, I'm gonna call B sub n something very, very similar to A sub n, but I'll know more about B sub n than I will A sub n. All right, so what I'm going to do is I'm going to call B sub n. A lot of times what you do is you look at the highest degree on A sub n. So I'm going to call B sub n 2 over 3 n squared. Now I know a lot about this 2 over 3 n squared. If you've studied series, you know a lot about this 2/3 times 1 over n squared. All right, so if you examine this B sub n, if you examine this, what you can turn this to is you can analyze, if you take that 2/3, you pull it out, you take 2/3, you pull out 2/3, and you examine the summation from n is 1 to infinity of 1 over n squared. One of the things that you'll see is that this is what's called a p-series. And whenever this term here is greater than 1, you know that this series converges. So if 1 over n squared, you're summing n as 1 to infinity, converges, well then 2/3 times that would also converge. So now what you know is you know that B sub n converges. You also know that if you look carefully at this, if you look carefully at this, if you were to maybe graph this, your B sub n terms, this denominator would be larger than this denominator. All right, so this denominator is larger than this denominator. So what that means is that this overall fraction, because it has a larger denominator, would be actually smaller than this fraction here. This is a larger denominator. This is a smaller denominator. That would make this overall fraction smaller. So you've got A sub n, which would be some series. And for every value of n, B sub n would actually be more. B sub n would actually be more at every value of n. Again, because this denominator is smaller. So B sub n would be greater. So what we have just determined is two very important things. B sub n is greater than A sub n. B sub n is greater than E sub n for every value of n. And we've also come to the conclusion that B sub n converges. B sub n converges. So if B sub n converges to some finite number, then it's safe to say that A sub n would converge. All right? So what that is called the direct comparison test. All right, so what we'd say here is something to the effect that B sub n is greater than A sub n. All right, with a series summing from n is 1 to infinity. B sub n is greater than the summation from n is 1 to infinity of A sub n. All right, so that's the case. And you also know that the summation n goes to 1 to infinity of B sub n, you know that this converges. You know, this converges because it's a P series. Well, if B sub n converges, then you can say that A sub n must converge. All right, so it's called the direct comparison test. All right, again, what this theorem says here, I don't know if you can see that, but it says if the series B sub n converges, then A sub n converges. All right, so that's our first problem. It's called the direct comparison test. We want to get through as many tests as we can. All right, so let's talk about another problem. This problem is asking if you have a series where you're summing n is 1 to infinity. All right, n is 1 to infinity, and you have 2 over 5n squared minus n plus 1. All right, so you want to know is if you continue to add a series of terms where you increment from 1 to 2 to 3 to infinity, will the sum of these terms end up being something finite? All right, so if it is, you call it the series is converging. If it doesn't, if your series continues to grow to a larger and larger sum, we call that a divergent series. All right, so let's use a different test here. The directions, you don't see the directions, but the directions here say use a limit comparison test. The limit comparison test. And that is on page 576 in my textbook. This idea of a limit comparison test says that if you take the limit as n goes to infinity of A sub n over B sub n, all right, and you get some limit L. You get some limit L. If that limit L, if it's finite and positive, both A sub n, if your limit is finite and positive, both A sub n and B sub n either both converge, or both diverge. Either both converge or both diverge. Oh, you can't see that. I'm sorry. All right, so one more time. You're going to take, you got the original problem A sub n. You're going to choose some B sub n, all right, that you'll know something about. You're going to choose a B sub n. You got to know something about that B sub n. All right, and then you're going to take the limit as n goes to infinity. And if the result of the limit as n approaches infinity is something finite and positive, both A sub n, either both A sub n will converge or A sub n and B sub n will diverge. So the best way to explain this is to do a problem. So let's look at this problem here. Let's look at this problem here, and we'll do it right over here. So what we've got is we've got this 2 over 5 n squared minus n plus 1. All right. So let's attack this problem. So let's choose a B sub n. A sub n is the original problem. 2 over 5n squared minus n plus 1. B sub n is something that you choose. It's an expression, it's a term that resembles A sub n, but it's an expression that you know something about. All right, again, what you're going to tend to do is focus on the highest degree in both the numerator and denominator. You're going to focus on the highest degree. So B sub n, we're going to choose 2 over 5n squared. All right, so we're focusing on the highest terms in the numerator and denominator. Plus, if you look at B sub n very closely, we know something about B sub n. All right, so let's reduce this a little bit so it becomes a little bit more familiar. If you pull out the constant, 2/5, and then you sum n is 1 to infinity of 1 over n squared, again, you've got another P series where this term here is greater than 1. When this term here is greater than 1, that's a P series that converges. Well, if this series converges and you multiply it by 2/5, you get something finite, which would mean that B sub n converges. That's important to keep in mind. So here we got B sub n. Let's just make a note. B sub n converges. All right, B sub n converges. Now what this limit comparison test, let me write that down so we all know what I'm working on here. So this is the limit comparison test. Limit comparison test. All right. So now what this limit comparison test says is if you take the limit as n approaches infinity of A sub n, which was the original problem, divided by B sub n, which was the expression that resembled A sub n that you know something about. If you divide those and you take the limit of the quotient, let's do that right now. We've got 2 over 5n squared minus n plus 1 divided by B sub n, which was 2 divided by 5n squared. Okay, so if we take the limit of this quotient, this is A sub n, the original problem, this is B sub n, we created that, and you get some limit that's both finite and positive, well, then A sub n will both either converge, or A sub n and B sub n would either both converge, or A sub n and B sub n would either both diverge. So let's evaluate this limit. All right, so what we have here is we got the limit as n approaches infinity of a quotient. Anytime you have a quotient, you can multiply by the reciprocal. So we got 2 divided by 5n squared minus n plus 1. And let's multiply by this reciprocal, the reciprocal of this. So you multiply by 5n squared over 2. All right. So what you experience here is you experience a cancellation of the 2's, and now what you have is you have the limit as n approaches infinity of 5n squared over 5n squared minus n plus 1. All right, you evaluate this limit. A couple ways you could do that. You could use something called L'Hopital's rule, or you could divide by the highest degree. You divide by the highest degree. In either case, what you'll experience is getting a limit of 1. You're getting a limit of 1. That would be your limit. So what I'd like you to be able to see is this limit comparison test states that if you evaluate the limit of the quotient and you get something finite and positive, 1 is definitely finite and positive, both a sub n and b sub n either converge, or you end up with a situation where a sub n and b sub n both diverge. Well, we've already established earlier that b sub n converges. So because of this test, we know that both, if b sub n already converges, we know that a sub n, according to this test, would also have to converge. So the way I'd write that is I'd say something to the effect is because both a sub n, both a sub n and b sub n must either converge or diverge. Okay, so because both a sub n and b sub n must either converge or diverge, okay, and it was already determined that b sub n converged. I had already determined earlier that b sub n converged. Then a sub n, the original problem, must converge. All right, must converge. So, sorry about that. So, the theorem, the test says that summation of a sub n and b sub n must either both converge or they'll both diverge. We determined that b sub n converged, and therefore we can say that a sub n must converge. All right. So these are this is a calculus 2 topic, second semester calculus topic, where you're examining series using different tests.